I thought they were on Google Drive.
Not anymore.
It didn't work last year. Like I would save them and then I wouldn't save and then
It
it
worked
would
for me.
disappear and
Remember I did the bleach thing?
What?
Oh, that's funny. Here we go.
I don't have a PayPal account, thank you.
What are we doing? We're taking derivatives of what? Integrals.
Integrals.
But.
The inverse.
Showing the inverse property between differentiation and integration, but we can't just say it's a derivative, it's an integral. Let's just cross them off and say that they don't matter because they do.
Can you do that anytime you want, really?
Well, only when you're directed to take a derivative.
No, I mean like, what you
Split
did
up
on
stuff?
20, yeah.
Yeah, I can split up stuff.
Just whenever
Wait,
there's
why?
like-
How do we know that 0 is in between sine and cosine?
We don't, but remember we have the property A to B and B to C. It doesn't matter what B is. It could even be backwards.
Oh, okay.
That's a good
And then
point.
as you go to save the bounds, or as you go to use the bounds, using the properties, it's going to end up perfectly
Oh,
perfect no matter what.
there was a question in homework that asked us to find a bound using our calculator.
Okay, well let's keep going.
Okay, so that's like a specific question. We need to finish the notes first. Okay. If we have time at the end, we'll have a work day with like questions on homework.
I'm sorry.
Question. If our direction is to find dy dx, do I want to take a derivative right this second?
Absolutely not.
No, because which one's in the wrong order?
Gosh.
So this one needs to become a
Negative.
good. Just flip it. Now it's about to write it the same again. 0 to sine of x. Did we say hi, Joyce? Did I start recording? Hi, Joyce.
Hey Joyce.
Okay, so then coming back. Now I want to go take a derivative. So I take the derivative of y. That's just dy dx. I'm going to take the derivative of this side. Wait, I can't. There's an addition. Just kidding. Sum and difference property. No big deal. Take the derivative of both, right? Cool. So I have, you guys tell me, what?
Sine x, negative sine x squared.
It's just kidding.
Negative
Times cosine. And I can write it the
Plus
snippy,
cosine.
don't be tricked by the trig notation, sine squared x, right?
Cosine
And then plus cosine.
was.
X squared.
Wait. Okay.
Oh, time.
Where do you get the sine? Negative
Why?
sine squared. Okay,
Oh,
so it's
well,
u
first
prime,
of all,
right?
we have to plug in
U
u,
prime.
so u squared, and then times u squared.
Okay.
So it's f of u times u prime, and so then it's t squared, but with sine of x instead, so sine of x quantity squared, which is sine squared of x, times u prime, which is cosine, plus minus.
0.
Well, yeah, you could put it in minus.
I'll just write 0 at this point.
Why?
Because it's going to be a value.
No. We're talking about the second integral.
What?
So you see how the integral from 0 to sine of x, and then now we're doing this, the one from 0
Oh,
to
okay.
cosine.
So then, once again, derivative of an integral, have to plug in the u, so it's going to be cosine squared times u prime, which is negative sine, so then we change it to be negative.
And then we get,
And then we could be super snazzy and like simplify stuff, or we could just say, hey, make it match B2, right? Okay. Now, what happens, that's a bit interesting, on number 25.
yeah, this is the homework I needed help with.
Yeah, it got weird right here, right?
I was like, what are you
Construct a function of the form y equals the integral from a to x of f of t dt plus c that satisfies the given conditions. So I have a derivative. They don't need me to solve for y without integration. They're saying, hey, you can take the derivative and you can throw them in an integral and just signify y. Just show me how to find y. Which is a good thing because cosine squared, how do you integrate that one?
You prime?
Yeah, it'd be
You could deal with the 5x. You
it'd be
could
2
deal with
cosine.
U and B?
It'd be 2 cosine 5x negative sine x times 5.
If we're deriving. But we're not deriving, we're trying to go backwards. The antiderivative, but we don't even need to find the antiderivative. We can say, whatever, to go from dy dx to get back, don't we just need to integrate? True? So we can say, okay, y is going to equal from the integral. Let's get back to the bounds in just 1 second. Cosine squared is our derivative, so he becomes our integrand, right? He becomes our integrand that we want to integrate to go back. X is our top bound, because we're trying to get to a function of x. But where are we going to start from to get to x?
7.
Why 7?
Is it 7? Do I have to plug in?
Just because it gives us a point.
It can think of this somewhat as our initial condition, not because it's at the beginning, but it is our single solitary clue, right? So we can say, okay, starting from 7 and going to x, well, hold on, if it's starting at 7, what if x is 7? I mean, I know x is 7 in the clue, but I mean over here. Because we're trying to build a function, basically. Construct a function, build a function. X could be 8 or 9 or 10, like the y value at 8 or y value at 9 or y value at 10. This could find y values even if we can't find the function itself. But what if the function was 7? What would this integral be? 0. So why do they show this plus c? Because I need to make it match. And so if x is 7, y of 7 would be 0, but I need it to equal negative 2, so I can say c is equal to negative 2. And so the crazy thing is you can take a derivative, you can take a rate, and even if you can't find the function, even if you can't anti-derive, you can find the values of the original function at any x value using this method.
So the negative 2 would be in all of them, no matter what the x is? Or only if it's x is 7?
The negative 2 makes this expression true at 7, and then going from 7 to any x, the integral is going to compensate.
And you
for
don't
this.
need to worry about the negative.
Well, he's
Oh,
in
it's-
there for everyone. So
That's
he's like our plus c, he's our initial condition, and then the integral starts at 7, starts at negative 2, and then builds off of that to get to wherever else it needs to go forward to back.
Got it.
Does that make sense?
My only question is, how did you, if you say, hey, let's make our initial point 7, and then say, hey, let's make our final bound 7. I mean,
I'm not saying make the final bound 7, I'm saying we're trying to construct or get to an original function without actually anti-deriving. Get an expression that can solve for the original function at different x values. And so in order to do that, we need to integrate, but we need to have some sort of numeric way of integrating. We don't just want the anti-derivative because we don't know him. At least not at this level. And so, if we don't know the anti-derivative, we need to be able to make a definite integral that would solve for the function values at 8, at 9, at 2, at negative 1, at 7. It has to work at all the different values.
so at both points.
So I'm just saying it has to work for 7 and all the other values. All the other values are fine, they're encapsulated in this x, and I'm taking the antiderivative cosine squared, but I had to start somewhere, so I started at 7. And so I'm saying, okay, I'm starting at 7, but this has to work when x is 7 as well. So I'm starting at 7, it has to work at 7. 7 to 7, the integral has no bearing. I need it to equal what value they told me it had to be, which is negative 2.
If you want to try and find out a different, like let's say now it happens to do a different point, would you plug in a different point for x, or would you change both bounds to be that point?
No, this function is defined. This is y in terms of x, so there is no redefining. This is the function itself. So if they said, hey, find y of 8, I just plug in 8. If they say find y of negative 2, I plug in negative 2. Without having the function itself, this would solve for all of those different values. And that kind of answers your question about why we only plug in there and not somewhere else.
If we were trying to put an integral into our graphing part, and it was an x as one of the bounds,
Well, you wouldn't be able to solve this for the general equation. That's the whole point. We can't find the antiderivative, but we can use this to find values. And then theoretically, I guess we could go ahead and make like a scatter plot of all these different values and try to find a function that seems to fit. But that'd be a regression. That'd be statistical data.
That'd be lit.
That'd be cool stuff.
I just find it interesting you can actually do a regression by hand.
A regression by hand?
Yeah.
Well, line of best fit is brutal. To do anything else, it's just going to get worse. Not impossible, but I mean, well, if you're doing a regression by hand, then you're saying you know what it looks like without ever graphing it, which I mean, I guess you could scatter plot by hand. Oh, you guys don't need to write this because we already did, right? The derivative of the integral. However, I wanted to show this to you really quickly because some of you might have wondered, once upon a time, why it's called the fundamental theorem of calculus. What's the big deal?
It's fundamental.
The big deal is difficult to over the equation because it says that every continuous function has an antiderivative, and it says the processes, whatever, of integration and differentiation are inverses of one another. And before that, it says that every continuous function is the derivative of some other function. I forgot that actually applied as well. So So if every function is a derivative of some other function, if every continuous function has an antiderivative, and if it shows that the two are inverses of one another, it kind of encapsulates all of the beginning of calculus, right? Derivatives, antiderivatives, and then the inverse nature of the two. Anyway, so that's why they think it's pretty stinking important. Now, there is a second part to the fundamental theorem of calculus. Our book says the second part. Last year we called it the first part, whatever. It's a part.
It's FTC.
It's FTC, the evaluation part. So we have the antiderivative part, and then we have the evaluation part. The antiderivative part has to do with the derivative of the integral is the integrand. Just got to be careful for when we have u. But the evaluation part says, sweet, definite integral from a to b of a little function f of x dx equals the antiderivative of b minus the antiderivative of a, which some of you have been using for quite some time and even cheating and using it early this year. We're going to go through and review and recap and make sure we're good.
Nothing wrong with cheating if you don't get caught. Mr. Halliday taught me that.
Seriously?
No, I'm trying to give way to my argument.
Oh.
Should I pause the video right now?
If he's gonna see it, you should delete this video and we'll start from the beginning.
Or you can just like
We're
take
gonna
out
ask
the
his questions again.
you can take out the
Yeah, just
the audio.
Well, I just cut out that one, those few seconds.
Yeah, we're
But he also said, no, not really. He was just trying to add weight to his argument. So.
yeah, they're nothing of a liar. Oh, by the way, did you ever ask Mr. Halliday about?
Actually, I tried yesterday, and then someone was talking to him after the meeting, and I was like, forget it, I'll try them. And then today he Instagrammed me.
What?
Why does he get the meeting and you guys don't?
No, he left after the meeting.
Yeah.
Oh.
He
He didn't stick
Instagrammed me.
around.
Cool kids.
Technically, we're-
Antiderivative means which function has the derivative of. Gerard, I know you've studied some of these rules, so hopefully we'll just get you better at them. And the rest of you guys, clean out the cobwebs,
I totally studied these rules.
polish up the silver,
like stuff.
get rid of the tarnish.
Or
What do we do to get x to the 3 halves, his original function? If he is the integrand, then he is the derivative, and who is his antiderivative? X to the what power?
squared.
5
Half.
halves
Oh, what?
And times
2 plus
2/5.
2 over 2.
times 2 over 5. Now, hold on, explain.
3, 2 over 2. Oh.
Plus
you
3 halves plus
add
Yeah.
1 to the
Yeah, yeah,
power
2 over
and
2.
flip.
Increase the power by 1 to decrease to the power rule, and then multiply by the reciprocal, so that when he comes down, constant's down, and then I subtract 2 over 2. Sounds like Carson. And I get 3 over 2 done. Now, our brain, don't make our brain work hard, guys.
Yeah, exactly.
Right? 5 halves, who is that?
Square root of
Square root of x
fifth.
to the 5th.
X to the 5th square.
Oh,
root.
True.
X there.
It's x squared.
Or, couldn't it be easier if it was x squared square root of x?
I'll take that.
Say that again. How?
2.5.
2.5.
So squared and then a square root. So you can go ahead and do 5 squared square root of 5 minus 0 squared square root of 0. Well, that's kind of lame, but that's okay. We got it. Don't forget the minus. And we end up with, that just cancels out. One of the 5's is going to reduce. And then we end up with 10 root 5. Done, so that's done.
Dun, dun.
Are we good?
No, you need to copy all that down.
Okay. Those of you guys that finished early, take it away.
What is that little squiggly above the 5?
Above the
What? Oh, it was me canceling out the second power because I reduced it with that 5. Does that make sense? Take it away, number 32, ln.
Oh, what are we No, oh wait, no.
I was trying to trick you.
Yeah.
1 over x. Did you do
We
x,
said LN, I
x
was like,
negative
I
2?
just-
Yeah.
and I looked up.
Yeah, exactly what you want to do.
If you're doing if it was 1 over x, which it was,
ln.
if no, could you do x to the negative 1?
No.
Or would that just be ugly?
ln. Because that'd be x to the 0 and then over 0 and that's 7 to 5. Only ln has a derivative of 1 over x. Sometimes it can be confusing, so if it's ln of x squared, then things get interesting.
These D's
My anti-derivers. So 2 seconds ago.
Still trying to trick us.
Sure.
I'm shocked.
What's my new power of my antiderivative?
70.
And I divide by a negative 1, which means just a negative, and then I take it from negative 2 to negative 1. Make it easy on your brain, right? Negative 2 over. Which one do you plug in first?
Well, negative 1.
Good, F of B. F minus up at the bottom. Showing negatives
So,
going on.
yeah.
There we go. So then 2 minus 1 is? Double check. So this is the easy stuff, right? So why on earth did I have it be a whole nother day? Why not just have homework due today?
Because this one's gonna be fun.
We have some more fun examples that come in. But first of all, just in case you've ever wondered why it's called the fundamental theorem of calculus, this part's important too. It says that an indefinite integral of any continuous function can be calculated without taking limits, what? Without calculating Riemann sums, what? And often without much effort. So long as an antiderivative of f can be found. If you can imagine what it was like before this theorem and before computing machines, when approximations by tedious sums were the only alternative for solving many real-world problems, you can imagine what a miracle calculus was thought to be. So, this is why the theorem deserves to be the fundamental, and the second one's important too. Okay. Anyway, kind of spiffy. All of these, where are they?
All the
If
things.
you know these, what should you know?
Those.
Those, because it's backwards, right? Now, most of these are hopefully fairly straightforward, except this one, but we just talked about him quite a bit, right? Powers, you increase by 1 and divide to offset the constant, true?
True.
Plus C only occurs when your integral is what?
Indefinite.
Indefinite, without that. Let's keep going. So then all of these, same dealio, these are the ones, Gerardo, you were asking about a second ago, or a couple days ago. Antiderivative is just think which function has the derivative of. What is the little bit of a trick when it comes to a this one, and a this one, and a this one?
Negative.
Yeah, because you have to say sine and say, wait a minute, the
Negative.
derivative of sine is a positive cosine, but the integral of sine is a negative cosine because cosine's derivative should have had a negative,
Shoulda, coulda, woulda.
right? So watch out for those signs. Should could would it?
Shoulda, coulda, did.
Watch out for those signs. Now these ones are easy, right? Because cosecant squared, you're like, yeah, it came from a c, and cosecant cotangent, yeah, it came from a c. Those ones, of course, should be negatives, but the sine, that's one that people mess up a lot.
What do you mean come from C, therefore should be negative?
Because cosecant squared comes from cotangent, and
The C's change.
yeah, in the
To the
beginning,
sine.
when we took the derivative of cosine, cosecant, cotangent, it was like, yeah, all the c's have negatives. So these have c's, they should be negatives, but the sine, you should,
Have a negative C.
well, for derivatives, sine had a positive, so that's the confusing part, because the integral of sine has a negative. And for cosine, the derivative had a negative, but the integral has a positive. So these two are the ones that are easily confused.
You know, integrals are a lot harder than derivatives.
Which is why there's the book of integration tables.
Oh, that is the thing.
That still does not encapsulate every function, because that only works for the functions that can be anti-derived. Some functions
I
can't.
think it's just that we practice
Our
deriving so much that it's hard to think backwards.
Yeah.
Our book is hurt.
But deriving is also finite rules. You can derive anything. You just have to work and carefully do it legally. Integrating, it's like, hey, here's some tricks, and there's some more out there that you're going to learn this year, a whole chapter's worth. And then guess what? Then there are these tables that kind of help you for ones that are even harder, and then guess what? There's some that can't even be integrated. But you're right. I think part of it is just not being as practiced with the other.
Our book is hilarious. This is a very brief
Hi.
video of integrals, and it's got like 3 pages of integrals.
So,
I looked at it and I was just like,
it's like you're silly
It was
goose.
like this.
Routine.
oh, just integrals?
Integration tables.
Dear God.
This
He was the best.
This from college.
You need to memorize all
Is
of them.
mine.
Saw him in
Is
Vegas.
mine. You saw what?
Dr. Teague in Vegas.
Literally?
Yeah.
What's that from?
He probably had the hardest class ever in 8th grade. He taught us like a college class.
Oh, yeah.
Sounds like Dr.
I heard
Trammell.
about that.
Yeah, but he
You
like.
guys literally just were on your phones cracking jokes with each other the whole time.
But the thing is, yeah, no one paid attention.
Yeah.
But the thing is, the average like test score was like a 30%.
Yeah, but it got curved like 100%.
Because I paid attention.
That's why Sam is.
He would do that with any of his classes, though, with physics and with AP Bio. He would, before all the other people were teaching them.
That's why Sam and Matthew didn't even care during the test because they knew it was gonna get curved, so they just had to get a few right.
So sad.
Sam Caddis?
Yeah,
Matthew Seals.
yeah, literally geniuses.
Okay.
Total area. Okay, this is a little bit of a struggle. I don't actually like the wording of the book. They say total area to describe this topic. I like much better area between. The nice thing is the problems they give you say the area between. And they say, hey, whenever you see the area and it's not described as net change, you have to think of it as absolute value. I say, let's not do that. But when we see the area between, then we think of it as absolute value. Absolute value meaning the above is positive, make the below positive, and add them all up. You are accumulating, in a sense, the total distance traveled. How does total distance traveled, my physics people? How does total distance traveled relate to displacement?
It's the addition of all the displacements.
The addition of the absolute value of all the displacements, right? Because
Yeah.
displacement can be negative. So the addition of all the absolute values of displacements, total distance says, I don't care if it was to the right, to the left, to the up, to the down. I just want to add them all up. How much did my odometer change? Okay? So, how does that apply to questions? Ready?
You take the angle separately, make it positive and add together.
Kind of. So let's work it out. How do we do with this one? Number 42. Find the total area. Okay, fine. It says total, but I like between. Good. Find the total area between the curve and the x-axis. No problem. Just integrate between -2 and 2, right? Okay. So then between -2 and 2, 3x squared minus 3, and then we go ahead and do our little dxy thing, and then we go ahead and say that's x cubed minus 3x. Maybe. -2 to 2, and then we end up plugging in 2, and we get 8, and then we get 8 minus 6, all minus -8 plus 6, and we end up with 0. Just kidding. It wouldn't have been 0. It would have been 16 minus 12, which would have been 4. Do you really think this thing only moved 4? If it has things like 16?
Probably not. To me,
What was our error in just integrating?
We didn't account for the fact that the area on the left.
You have to go between the x-axis, right? You have to find out
Where's
where
the
it is.
intercept?
-3. So it's a negative.
So if I just did the integral from -2 to 2, if I plug in -2, technically that would end up being 4 and 12, and 12 minus 3 is, so -2 somewhere over here. And then +2 somewhere over here. When I take the integral the normal way, it says, hey sweet, a positive number, okay, plus a negative number, plus another negative number, plus another positive number. This graph is not to scale. Okay, so,
Oh, I see what you're saying.
because it would have been 4.
We need to take it in as the positives because we want total displacement, right?
So what I need to do is think about this in terms of, hey, that's great, hey, this needs to flip, and then hey, that's great. So how do I flip an entire portion so I can say positive plus positive plus positive?
Absolute value?
Absolute value. So I need to think about this instead of, that's displacement. That's displacement. It's going to end up 4 to the right of its initial starting point from -2. I need to go ahead and take the integral from -2 to 2 mathematically, absolute value of 3x squared minus 3 dx. For my kiddos from last year and this year, am I going to be able to maintain the same bounds, -2 to 2, let's go? No. Because from -2 to negative, where's my intercept? 1? Yeah. From -2 to -1, it stays the same. From -1 to 1, it flips, and from 1 to 2, it stays the same. So our process would be, now in this one, we can look at the graph, right?
So it'd be -2 to 1.
Our process would be, looking at the graph, we're going to go ahead and keep -2 to -1, keep it the same. It's going to work out just fine the way it is. And technically, if we're super spiffy and we think about symmetry, couldn't we just double him? Right? And he would get both of the ends, both of the tails, because this is symmetric about the y-axis.
And then plus
Mhm.
-2.
Why
No,
does
wait,
it
-1 to 1.
Why does 2 come out?
It didn't come out. Because x squared is symmetrical, so the area on the left side of the left end, behavior, whatever, is going to be the same as the right.
So if
So
I
you
just
can just
double it,
multiply
I
by
can
2.
only have to do it once. Does that make sense? If I find this area and double, then I only have to find this one integral, double it, and then, why am I saying minus?
Because you have bounds from
This is gonna end up being what?
Negative.
And so if I do minus, what's it gonna make it?
Positive.
So then I end up with, this gets a little bit messy, and now all of my displacement stuff is in the way, so I'll get rid of him. He wasn't very helpful anyway. wanna get, and we already talked about x cubed minus 3x, right? So we can say
X cubed minus 3x.
negative 1 cubed minus 3 times negative 1 minus, double check me, x cubed minus 3x, minus negative 2 cubed minus 3 times negative 2. Sure?
That is so much.
Mm-hmm. Hang on. A negative x cubed minus 3 times 1 minus negative 1 cubed minus 3 times negative 1. There we go. Does that look right?
Yikes.
So negative 1 cubed would be a negative 1, negative 1 plus 3, that's just going to be a 2, minus negative 2 cubed is negative 8 plus 6 would be a negative 2. 2 minus a negative 2, 2 plus 2 is going to end up being 4, minus 1 cubed minus 3, it's going to be a negative 2, negative 1 cubed, negative 1 plus 3 is going to be a 2. Negative 2 minus 2 is a negative 4, and negative 4 times a negative is going to be a plus 4, which is going to end up being, did anybody check it?
Why are you adding them?
Because it was a negative minus a negative.
It's negative 2 minus 2 is negative 4, but it had a
Yeah,
minus
that's
in
not
front, so
calculated.
minus a negative will be a positive.
What's up?
No, I mean, like, why adding the integrals?
Oh, because I'm taking this area plus this area. So I'm saying plus, but I have a negative in there in order to offset the negative area and make the negative area positive. Which you can see happen here, because this area is negative 4 and minus a negative. I changed it to positive, and there we go. So instead of doing 8 minus 4 is 4, it's 8 plus 4, which is 12. Thanks for double checking. Wow.
So we're supposed to have to look at the graph to.
Well, in this
No,
one we did.
Find the zeros.
Don't worry, we'll summarize the next one in the next slide. Hang in there. Did it work, George?
Yeah.
Okay. Oh no! What do we do here? Total area between. Okay, it's all positive. There's no flipping of signs, but what do we have to consider?
The
Two different functions.
Because, right? So how would I write this problem? I'm not going to take time to solve it, but how would I write it?
The integral, no, yeah, the
From 0 to
integral
1
from 0 to 1 of
square root.
root x dx plus the integral from 1 to 2 of x squared dx.
Cool?
Burp to burp. Misty helped me with that one during the picture.
Yeah. Mr. Will was so funny. George needs some help. And I'm like, what? What happened? Like, what's wrong? And he's like, and I don't know, he was saying something cryptic. I looked over, I was like, he's doing calculus. And he was like, yes. It's like, oh.
Did you take out a whiteboard to teach?
I took out a whiteboard, well, because I saw Mrs. Leanne, I'm like, oh, whiteboard, great idea. So I came running back in. I just grabbed a big one, because it was right there. In theory, I should have like gone over and grabbed all the little ones, and I could have like had them write problems and work in groups on them. So I just wrote one problem, and then I used my emergency red card with my expo, because I had 2 expos. And so I would just give them to groups, and they were working on a problem, and I'd switch them to a different group.
So I was laughing so hard when I saw Mrs. Leon still teaching. I was like, this class.
It was awesome.
What?
I wanted to, and then I was like, I didn't bring enough whiteboards.
What was she teaching?
AP Chem. That's why.
Okay, so let's talk about absolute value in general.
I hate absolute value.
But wait,
Zeros.
Gerardo, what if we didn't want to keep going back to the graph, because just to say it could be an absolute value of a nasty function whose graph we don't want to find? What can we summarize as the process for how to solve integrals of absolute values without considering really the graph at all?
Find the zero, and then take away the
Where an absolute value hits the y-axis is where it could be flipping. Like it could hit and then supposed to go negative, could flip up to be positive. So if I find the 0, is there a 0? Yes. 2. Is it within the bounds? Yes, it is. Then I just go ahead and take the integral and say, hey, I need to split up there. Without knowing the graph whatsoever, I mean, I could picture it really fast, but try not to picture it really fast. Just splitting up at 2, I can say, fine. whatever the integral is in between this region, if it's a positive, I want to keep it the same, and if it's a negative, I want to flip it. I can pull the absolute value out. Now, I'm not pulling it out of the integral from -1 to 3. I'm pulling, or I'm setting that area, taking the absolute value of each of these areas, because then I'm saying, hey, I'm splitting up at the only places where it could flip from a positive value to a negative value, so where the area could flip from a positive to a negative. You're just being safe and you're not having to think about the graph whatsoever. Split up at the zeros and take the absolute value of each, which Gerardo should kind of make sense in the sense of if you're summing together all the different displacements, it's in between all the different stopping points. So the zeros.
Just split it up at the zeros, do absolute
And then you have
value.
to do absolute value. So it follows what the physics would teach you to do. Does that make sense?
Oh yeah, I just don't want to do physics anymore.
Calculus is
Which is not until college.
Physics is calculus.
Does that make sense?
It's great, but
Why do you have to do physics to begin with?
because physics is actually interesting, but if you have a bad teacher, it's really hard.
You have an
Not so
advanced teacher
Okay,
that stretches your mental capacity.
So that way your brain becomes all floppy and has scar tissue in it, and it's incapable of being working like when you were a child.
well,
It's
let's
like
just
worn
say
out elastic. Okay, there you go.
he taught the concepts well, but when it comes to examples, he did like the basic plug stuff in.
Yeah, and then it was hard to apply to other things.
Mm-hmm. But I got the concept really down, so.
Now, this is where the AP loves to test you. Now, we are in BC, so it doesn't mean necessarily this is going to be one of the AB/BC FRQs because we're only getting 3 that are AB-ish. The rest of our 3 are BC-ish, which means having to do a series or parametric or polar. Or what else? Harder integration, I suppose. Usually series, parametric, polar. Maybe something to do with a vector.
We're getting back to parametric and polar later, right?
Chapter 11.
We've done derivatives, but we haven't done integration.
No, we didn't derive a polar.
Yeah, we did. It was like review.
This is dr d theta.
DRD,
dr d theta, right? It's just like a regular.
no, that's when you're taking the derivative with respect to theta. What if you're trying to find dy dx of an r equals f of theta? Didn't we take the derivative?
No, we didn't. We didn't.
I remember taking,
Because it works just like parametric.
we took the derivative.
So parametric is dy dt over dx dt, and polar is dy d theta over dx d theta.
dy d theta over dx d theta. I don't remember.
Maybe we
never
just
went
did
over
the-
that. We
maybe-
didn't do it. We only did parametric. We didn't do derivatives of polar.
Muy interesante.
We'll get back to it.
We at least reviewed polar though. We did the pre-cal polar stuff.
Yes.
I thought we found hadn't done derivatives.
Oh, is this a first one?
Basically, what if you're given a function defined as an integral of another function?
Oh.
And you're given the graph of the integrand.
Then we turn it up.
And you're given the graph of the integrand.
This one was fun on homework.
That's the
No, this was the last problem. That was we were talking about 75. It was kind of like this. Actually,
There were 2 other ones that were like this too. There were 50.
Yeah, it was right around here, wasn't it?
oh, there's
58.
yeah.
58.
There you go, 58. That's the other one I was looking at. I was just like,
Okay. Here we go. Letter A. What are we doing? H of 0. H of x. H of x when x is 0.
H of x is 0.
Gerardo, this is your question. Where does 0 go?
H is 0. Oh, yeah, the 0 goes on the top.
The 0 goes in the top down, right? That's the only place it goes. So 0 to 0 of f of t dt. Okay, letter B. On what interval is h increasing? Take a calculus term, and before giving any answer, describe to me how this relates to f.
It would be. It'd be just f, just the integrand. It'd just be
Why?
integrand. Because
Connect the dots.
if you derive both sides, it cancels and it'll just be the integrand.
Good.
f of x.
When h prime of x, which equals who? Deriving both sides? Uh-huh. Okay, so see, so far all I'm doing is stating a forever card. I'm just saying, oh, h is increasing when h prime, who is h prime? Oh, f of x is positive, which occurs, okay, so when is f positive?
0 to 6.
0 to 6. I didn't already give all my justification? My explanation? My answer's done. So letter C, you guys take it away.
Should it be a closed interval for the 0? No.
Ooh. Yes, thank you. Why would it be a closed interval at the 0?
Because that's our domain, right? 0 to 12.
Not because it's the domain. F has to be positive, right? Which does not occur at 6, because F is 0 at 6, but what's going on at 8?
It's positive.
F is positive, so I have to include 0. Okay, letter C, concave up. You guys, try to go ahead and write the statement similar to I did, similar to how I did.
When it asks on the interval, is the graph of h concave up? Is it talking about, it's just talking about h, not
Yeah.
that graph, right?
Right. It makes it sound confusing, but when it says the graph of h, you just have to say, okay, they're just talking about h himself. So try to write it in your best, not gonna let the AP guys take any points away from me, version. You're answering the question, h is concave up. When? And which occurs?
Oh, you're right. Why? That's so confusing.
Ish, I had to approximate. Ish. I had to approximate, make it look a little bit closer.
Oh,
That's
It
it's
fine.
wouldn't be 8, it would be like 9,
I got 8.5.
I drew my graph wrong.
maybe 9.
Is it okay if I do that 8.5? No,
Why is it 9 to 12? Because remember, f prime is the slopes of f, right? F prime are the slopes of f. So where are the slopes positive? Well, the slopes are positive on the interval 9 to 12.
And 12 is open because of 0. Right, it's the 0, right?
Because the graph ends there, so it's not still increasing, right?
You can't include 9 because 9 is a horizontal tangent. Technically, I suppose you could include 12 if we use the definition of a closed interval. Meaning that you only have to come from one side, and coming from one side, the slope is positive. I guess maybe we should include 12. But technically, once again, we really don't, I haven't seen them take off points for that before, but it's probably smart to do. Is h of 12 positive or negative? Wait, what? H is an integral. H of
So the
who?
area.
H of 12. So he is area. Area from what? Starting at 0, moving to 12. So starting at 0, moving to 12. You can't actually find it. You don't know the function, but you can
But that's
say that
h
this is
prime.
to scale and say, hey, is this one bigger than that one, or is that one bigger than that one?
But that's h prime, isn't it?
Area is h.
But the graph is h prime.
Right.
So we can't, can we be estimating?
Remember, I can think about the area as the displacement or the change in h. Does that make sense?
No.
We know that h of 0 is 0. So I know that-
Because in this place.
because we were able to plug in 0, we were able to see the value. So I know it starts at a value of 0, and I can look at my displacement and say, okay, was the overall displacement positive or negative?
But that's not H's displacement, that's H prime's displacement, isn't it?
No. This is the graph of the derivative. Oh, I see what you're saying. No. The H is the area under F. See? H is the area under F, because it's the integral of F. There you go. So since H is the area under F, or H is the area under H prime,
Okay, I see what you're saying.
there you go.
Yeah.
Then the overall displacement is positive, right? Why? Because positive area wins. So if it's positively displaced from 0, well, an H of 12, since H of 0 equals 0 and H of we could say something about the area, the positive area is greater than the negative area.
Would that be sufficient to say that the area above the x-axis is greater than the area below?
I might go, yeah, you could say it that way. They take explanations. You could also say that the area from 0 to 6 is greater than the area from 6 to 12. That could be another sufficient way. They just want to see something where you know that the positive displacement is greater than the negative displacement, so it's going to be an overall positive change.
6.
6 is the 0. So this area, the positive, is greater than this area, the negative. So the positive displacement is greater than the negative displacement. Letter E, where does it achieve its maximum value? Yeah, at 6. How come? Because it increases to 6 and then decreases. That's the only place where its max will occur.
Why not end points?
Think about the behavior of the function. It's strictly increasing from 0 to 6 and strictly decreasing from 0 to 12. So at 6 it's going to be higher than at 0, and at 6 it's going to be higher than at 12. Does that make sense? We should justify it. We're talking about AP style, but for right now, since time is running short. And letter F, where is it going to achieve its minimum value?
At 12?
No.
No.
Zero.
0.
Yes. Why?
Because the area is
The
greater
amount,
than 0.
good. The amount it increases is greater than the amount it decreases, so then it must have been at its lowest point at h equals 0. Or at x equals 0, sorry. You guys have a couple of these for homework, so we'll make sure that you justify them properly for the AP tomorrow. Sound good? Okay. And then, what? We're done. Does that sound good? Okay. So since we do have 45 seconds, I'm not sure if I can properly justify. We'll talk about the justifications for E and I tomorrow. So we have to see proper justifications for E. Huh?
We can leave just, like, we can find a point and then leave the justification there. On you, is that what you said?
An example we did, but see if you can think about how you would properly justify. And then we'll check it tomorrow as a part of homework. We'll zero in on this. Are we good?
Yeet.
Wow, 15 whole seconds, kiddos.
So,